An elevator with a mass of 17,000 kilograms accelerates upward at a rate of 2 meters per second squared. What is the force exerted by the cable on the elevator? Okay, in order to do this problem, the first thing we're going to do is draw a picture. In this case, a free body diagram. So off to the side, draw a little dot representing the elevator and ask ourselves what forces are acting on the elevator. Well, there, of course, is the gravitational force because the elevator is near Earth's surface. And then there's going to be the force of tension acting in the upward direction for the cable. Okay, we don't have to worry about a normal force here because there's no surface. There's no frictional forces, again, no surface, but we do have the gravitational force and the tension force. Okay, so we've got our picture. Then we're going to go ahead and write down our givens. Well, what do we know? It says an elevator with a mass of 17,000 kilograms. So I'll write that down. The mass is 17,000 kilograms. And it accelerates upward at a rate of 2 meters per second squared. So we know the acceleration is in the upward direction, which we let be positive, so I'm just going to leave it positive, meters per second squared. And the question says, what is the force exerted by the cable on the elevator? Well, we know that the elevator is accelerating, okay? So we know the net force is going to be equal to mass times acceleration, Newton's second law. So let's go ahead and write that down. The net force, and this is going to be the net force in the y direction. Simply, there are no forces in the x direction. So the net force overall here is going to be in the y direction. And that is going to be equal to the mass times the acceleration. Again, Newton's second law. So let's go ahead and look at that. We know the mass, we know the acceleration, so we can find the net force. Something else that we know is that the net force means you take all the forces and you add them up. Well, let's go ahead and do that as well. We'll make that equation. There's a gravitational force acting in the downward direction, so I'm going to make that negative, as we say that downward is the negative direction. And again, the net force means add them up, so I'm going to add that gravitational force to the tension force. Now I've got two equations up here. It's good that one of them has what I'm trying to find because I am trying to find the tension force. Okay? And when I wrote the first equation, I didn't have a tension force in there, but I do in the second one. Okay? So now we can go ahead and set these two equations equal to each other because they are both the net force in the y direction. So I can just kind of substitute this in for that. So the mass times the acceleration is equal to the gravitational force, which again we make negative because it's going down, plus the tension force. Now I look at this equation. I know the mass, I know the acceleration. I do not know this gravitational force, and I won't be able to solve the equation until I only have one unknown. So I need to find the gravitational force. Luckily, that's something that we've been doing for a little while, fairly simple. The gravitational force is the mass times the gravitational field constant, 9.81 newtons per kilogram. So we can go ahead, substitute in over here, and solve. So the gravitational force is equal to our mass of 17,000 kilograms times 9.81 newtons per kilogram. Multiply that out, we'll get our gravitational force is 166,770 newtons. And now we can go ahead and start substituting in. So let's go ahead and substitute our mass in. So we have 17,000 kilograms multiplied by 2 meters per second squared is equal to the gravitational force, and again we're going to make it negative because it points downward, so negative 166,770 newtons plus the tension force. Go ahead on the left hand side, we can simplify that. multiply those together. 17,000 times 2 is 34,000 is equal to negative 166,770 plus the tension force. Add 166,770 to both sides. And we end up with our tension force is equal to 200,770 newtons. And so that is how we find our tension force.